So the work energy theorem is a relation between the work done on a system and the change in energy of a system. In its simplest form, it looks like this. The work done is equal to the change in the kinetic energy. Later we'll write this as the work done is equal to the change in kinetic energy plus the change in potential energy. But first we're going to derive it this way with just the kinetic energy and the work. So if you remember this formula from chapter 2, V final squared is equal to V initial squared plus 2A times X final minus X initial. Right, this is an equation that came from our study of kinematics in one dimension. Right? And so we're going to work with this equation a little bit. First, we're going to call this distance d, the distance traveled. Right? And then we're going to solve this equation for the acceleration. Right? And so we're going to write this as V final squared is equal to V initial squared plus 2A times d. Right? Or we can say V final squared minus V initial squared is equal to 2AD, or we can say the acceleration, dividing both sides by 2D, is equal to V final squared minus V initial squared over 2D. Okay. And we're going to use this equation to sort of work our way to a relationship between work and kinetic energy. We haven't even defined the kinetic energy yet, but we're going to get there. So now we're going to start with this equation. I'll erase this. So here's my equation. I'm starting up here. And if you remember, so now I have my acceleration. If you remember, we can say from Newton's second law, the net force is equal to the mass times the acceleration. And so we can replace the acceleration in this equation with this, and we can say, look, F net is equal to the mass times this stuff, V final squared minus V initial squared divided by 2D. Now we can multiply both sides by D, and we get F net times the distance is equal to the mass times V final squared minus V initial squared all over 2. Or that's just 1/2 m V final squared minus 1/2 m V initial squared. Right, and so I get this formula, F net times distance equals 1/2 m V final squared minus 1/2 m V initial squared. These things we call the kinetic energy. So this is the kinetic energy final, and this one here, without the minus sign, is the initial kinetic energy. An object of mass m moving with velocity v final has 1/2 mv squared of kinetic energy. Right. If you remember, the net force times the distance is just the work. So this gives us the work done on the system is equal to KE final minus KE initial, or the change in kinetic energy. In other words, when we do work on a system, when we apply a force over a distance, right, we change the velocity of the object that's being acted upon. Now this is the net force, so you have to add up all the forces. If I'm raising an object against gravity, gravity's pushing the other way. It could be that even though I'm pushing, the net force is 0 if the object's moving at constant velocity. But the work, the net work done, is the change in kinetic energy. So let's do an example or two. What is the kinetic energy of a baseball of mass 150 grams or 0.15 kilograms traveling at 30 meters per second? So our formula for kinetic energy is just Ke equals 1/2 mv squared, right? And so this would be 1/2 times 0.15 kilograms times 30 meters per second squared. And when I multiply all those together, I get 67.5 joules, right? And I can say, well, what would his kinetic energy be at 60 meters per second, right? That would be a really fast baseball. Once again, kinetic energy is just 1/2 mv squared, but if you notice, our velocity is twice this one. And so if we wanted to, we could say, well, this is just 1/2 m times twice the previous velocity. I'll call this times v1 or something like that for this guy. Right. All squared, or that's just 4 times 1/2 m v1 squared, right? And so that would just be 4 times this energy, which is 270 joules. So the kinetic energy goes as the square of the velocity. And so if your velocity is twice as big, you're carrying 4 times as much energy. Right. This is really important in cars and things like that. When they have accidents, when you're going faster, twice as fast, you don't just have twice as much energy, you have 4 times as much energy. And that's where all the damage gets done. So in this example, we have a soccer ball that is traveling along at 5 meters per second when it is kicked, and the direction is going by a force of 10 newtons over a distance of 1 meter, right? What is the final velocity of the ball? So here's the ball, right? And it's a soccer ball. I don't know how you draw a soccer ball, right? And here's a foot kicking it. It's already traveling at 5 meters per second. But here's a foot kicking it, right, this way. It's applying a force to the ball. And as the foot follows through, right, here's my foot following through, and here's the ball continuing on its way. This is V initial, and this is V final, right? And the distance over which the foot was in contact with the ball was 1.0 meters, right? So here's my force F that's applied to the ball, and it's applied the whole time the foot is in contact with the ball. Well, maybe it goes up to here, right? It looks like the ball's already left by a little bit. But so the foot is in contact with the ball for a meter, right? And during that time, it changes the velocity of the ball. So to start this problem, we begin with the work kinetic energy theorem, which states that the work is the change in kinetic energy, and that's just Ke final minus Ke initial, or we can say the work is equal to 1/2 m V final squared minus 1/2 m V initial squared, right? But what we're looking for is V final in this problem, because they gave us the initial velocity, 5 meters per second, and the mass, and the force and the distance, but they didn't give us V final. And so we can solve this for V final. We get 1/2 m V final squared is equal to the work done plus 1/2 m V initial squared. If we want to solve for V final, we need to multiply both sides of this. I guess I can do it this way, by 2 over m, right? And this gives us V final squared is equal to, and if I distribute that, I get 2 times the work divided by the mass, right, plus V initial squared. Well, we remember that the work done is just the force times the distance, right? That's how hard his foot was pushing times how long that force was in contact with the ball. And so this becomes V final squared is equal to 2 times the force times the distance divided by the mass plus V initial squared. Well, on the right-hand side, we have all of these numbers. This becomes 2 times 10 newtons times 1 meter divided by 0.5 kilograms plus 5 meters per second squared. And so that says V final squared is equal to 2 times 10 is 20 times 1 is 20 divided by 5 is 40. A newton meter is a joule divided by a kilogram, so this is 40 meters squared over second squared plus 5 squared is 25, 25 meters squared over second squared. And so this is 65 meters squared over second squared, or the final velocity is about 8.1 meters per second. Sorry, the final velocity, no squared there. The final velocity is 8.1 meters per second. So the ball was traveling along at 5 meters per second. The person kicked it with a 10 Newton force. The force acted over a distance of 1 meter, and the final velocity of the ball was 8.1 meters per second. So now we're going to talk about the work done by a varying force. If you remember, our original equation for work done was force times distance times cosine theta. But in a straight line, we just said work equals force times distance. And so in the previous problem, we said, well, you know, if F equals 10 newtons, right, and D is equal to 1 meter, then the work done is just 10 newtons times 1 meter, or 10 newton meters, which is 10 joules. Right, the question is, what happens if the force is changing as the distance is being traveled? And so even with the previous case, if the person's foot was not exerting exactly 10 newtons the whole time, if it was decreasing as he was following through over this distance, or if instead of talking about a foot, you were talking about a spring, right, where the force is greater the more the spring is compressed, and less as it gets towards equilibrium, you can't just multiply the force by the distance anymore, because you don't know what the force is. The force is varying over that distance. So let's look at the example of a ball pressed against a spring and then released. So I can take a spring and I can compress it, and then I can release it, and it'll push against a ball, right, or some other object. And so here's my ball, here's the spring in the relaxed position. And then I compress the spring at distance x. And since the force due to the spring is proportional to the distance, now normally we would say it's equal to negative kx, but we're just going to look at the magnitude here. We're just going to say, look, the force is proportional to this distance, and so the force that the spring is pushing right now is with k times the distance, right, k times this distance. And then as the spring pushes the ball back out, the amount the spring is away from its equilibrium will decrease, so the force will decrease. Right? And so the ball gets accelerated this way. Its velocity here is 0, right? Because I've just released it. And then when it gets to here, it'll go sailing off in this direction, or rolling off in this direction. And then the spring will be back in its equilibrium position. If we're interested in the force that the spring is applying as a graph versus distance, you can kind of see, I tried to make it look like, so here's this position, right? And here's the compressed position. And so when the spring is all the way back here, right? When the spring's been fully compressed, the force it applies is K times X. And so that's here on my graph. And then as the spring moves outward, the force it's applying is smaller and smaller because the distance it is from equilibrium is steadily decreasing, right? Eventually, when the spring gets to here, now the ball is leaving it, the force due to the spring is 0, right? And so at various times along here, as we move along this curve, as the spring moves forward, the force is steadily decreasing. And so when we say the work is equal to the force times the distance, or in this case, the force times X, we're not sure what force to put in. Do we put in this force, or do we put in this force? And the answer is we have to put in an average force. And so the average force is, we can say F average is equal to F initial plus F final divided by 2. Well, the initial force was just K times X. That's what we said all the way back here, if we compressed it at distance X. Similarly, the final force is 0, that's this force, right? And then divided by 2. And so it's just 1/2 kx, right? And now we're saying, look, instead of saying we have a big force here and a little force here, we're going to say we have an average force all the way across, right? And so for this case, we can say, look, the work done is the average force times the distance. In this case, that's equal to 1/2 k times x. That's my average force. And the distance that I moved is also x. The ball was in contact with the spring over this whole distance, which, as we set up here, is x, right? And so we get 1/2 k x squared is the work done. So when a spring has been compressed at distance x and released, the work it does is 1/2 kx squared. So let's do an example. Remember, the work done by a spring, right, is 1/2 kx squared. X is the distance it's been compressed, right, and then it's released. And we get the 1/2 because we're taking the average force, like we were saying in the last section. So here's our problem. A spring with spring constant 100 newtons per meter is compressed by a distance of 0.1 meters, right? And so it's compressed. Had to be a bigger spring than this, but you get the idea, right? A toy car is then placed against the spring. Its mass is 250 grams or 0.25 kilograms, right? And then the spring is released. So just like in our previous picture, and the question is how much work is done by the spring on the car, right? And we just get, well, the work done is 1/2 kx squared, or 1/2 times 100 newtons per meter, right, times 0.1 meters squared, and this comes out to 0.5 joules. So that's the work done by the spring. And so this, if you remember our work kinetic energy theorem, is equal to the change in kinetic energy of the car. Okay. So now we can ask question B, what is the final velocity of the car? If you remember, we said the work is equal to the change in kinetic energy, right? This is KE final minus KE initial, right? But the car starts at rest against the spring, right? Because when we push the spring back, we release it, right? And so when it starts, its initial velocity is 0. And so if we want to, we can write it this way. We can say it's 1/2 m v final squared minus 1/2 m v initial squared. But this term is 0 because v initial is equal to 0, right? And so that just says the work done is equal to 1/2 m times v final squared. All of the kinetic energy is stored in the motion of the car, and so we could say v final is equal to squared is equal to 2 times the work divided by the mass, right? Or v final is equal to the square root of 2 times the work divided by the mass. But we just said that the work done was 0.5 joules, so 0.5 joules, right? Divided by the mass of the car was 0.25 kilograms. And so this is the square root of 1 joule over 0.25 kilograms, right? And that's equal to the square root of 4. If you remember, a joule is equal to kilogram meters squared over seconds squared. And so this is just 4 meters squared over seconds squared, or V final is equal to 2 meters per second. That's the final velocity of my car. So let's go back and look at our work equation for a spring again. Again, a spring has a varying force because to compress it just a little bit takes a small force, but as you compress it more and more, it gets harder and harder to compress it, right? And so to calculate the work done, we took the average force and multiplied it by the distance, and that's why we get a 1/2 kx times x. And so this is the formula for the work done by a spring with spring constant k compressed to distance x and then released. Notice if we compress it twice as far, so if we say, W1 is equal to 1/2 k x1 squared, right? And then we decide, no, next time I'm going to press it by this distance, which is twice x1. I get W2 is equal to 1/2. It's the same spring constant, right? Times x2 squared, right? But that's just 1/2 k times 2x1 squared, which is 4 times 1/2 k x1 squared, which is equal to 4 times W1. What this is saying is that if you compress a spring twice as far and release it, it does 4 times the work. And that shouldn't be too surprising because it takes a whole lot more each little extra distance you push it in to push it that additional distance. All of that second x1 of distance, right? If I take my spring, say this is my spring, right? And first I compress it to here, right? And then I compress it to here, right? The whole distance from here to here takes a greater force than any force in this distance. The force is just constantly increasing, and so I would expect more and more work to be done as I go. And so the work done compressing a spring and then releasing the spring goes as the square of the distance.